we generate an almost unimaginable amount of data every single day. Like it's gotten to the point where we're creating something like 2.5 quintillion bytes every single day.
Every day.
Every single day.
Wow.
That's a 2 with 18 zeros after it.
And the wild.
So finding new and more efficient ways to store all of that information, it's a challenge, to say the least.
Wow, for sure.
And that leads us to today's deep dive, where we're taking a look at how we might be able to use fractals, of all things, and artificial intelligence to store data.
It's such a novel approach.
Yeah.
It's really out there. And what's interesting about it is we're not just talking about some theory here.
Yeah.
We're going to be looking at actual code.
Real deal code.
Real deal code that demonstrates how this could work in the real world.
And when I first saw this code, the first thing that jumped out at me, and I don't know if you had the same experience, was this concept, this idea of an exponential canopy.
Oh, yeah, for sure.
Which just sounds so cool.
It sounds like it's straight out of Star Trek or something.
Right.
Some science fiction novel, yeah. But it's based on some pretty elegant math. And, one thing I think is really cool about this is that it's based on the efficiency of the natural world.
Yeah.
Nature has already kind of figured this out.
Right.
And, we're playing catch up a little bit.
Oh, sure. Yeah.
The code generates this 3D fractal structure, this canopy, and it actually mimics the way that sunflowers or pine cones, things like that, are structured.
Okay.
Where they use something called the golden angle to pack as many seeds or scales as they can into a really small space.
Packing efficiency.
Yeah, packing efficiency. It's all about the packing efficiency.
Yeah.
And that's what this code is doing. It's basically saying, how can we arrange data points in the most efficient way possible using this principle?
So instead of branches, we have these beta points
Yes.
that are kind of spiraling outwards and upwards.
Yeah.
But then the question becomes, how do we actually get from these fractal patterns to storing actual usable information? Like, how does that leap get made?
Right. And that's where the AI comes in.
Okay.
Right? So this is where it gets really, really cool. The code actually uses a type of AI called a neural network.
Okay.
And neural networks, these are really powerful tools. They're based on how our brains work.
Okay.
And they learn by example. In this case, it's being trained to encode and decode data by taking data, whatever that might be, and mapping it onto the points of that fractal structure that we talked about.
So we're not just storing data in a linear fashion, like, say, on a hard drive.
It'd be very inefficient.
Yeah. We're talking about spreading it out across this three-dimensional structure.
Yeah.
Doesn't that seem like it would make it more complex, though, to access a specific piece of data?
It does seem that way, but that's the cool thing about the neural network. It doesn't actually access information in a linear way.
Okay.
It's not going to point to point to point. It's looking at the relationships between the data points on that fractal.
Okay.
So I always think about it kind of like, imagine you're navigating through a really complex maze.
Okay.
Right? At first, it's like, how am I going to get from point A to point Z?
Right.
But over time, as you learn the maze, you know the shortcuts, you know the pathways.
You see the patterns.
Exactly. The AI does the same thing. It learns to navigate that fractal structure and retrieve whatever data it needs.
So it's learning the language
Yes.
of this structure.
It's learning the language of the fractal.
It's figuring out how to put it on there and then pull it back off.
Exactly.
That's exactly what it's doing.
That's pretty incredible. Okay, so we're encoding data, we're decoding data. What about the problem of data corruption, though? I mean, we all know things can go wrong.
Right, of course, yeah.
Storage devices fail. So surely this system, however cool it might be, has to have its own set of vulnerabilities.
Sure, yeah.
What happens if part of that structure gets damaged somehow? So this is where I think one of the most ingenious aspects of this code comes into play.
Okay.
And that's the idea of error correction. You see, data isn't just stored once on this fractal. It's actually stored in triplicate. Triplicate.
Meaning each piece of data exists in 3 different places on the fractal.
3 different places on that fractal. That's exactly right.
Wow.
It's like having backup copies built into the structure itself.
Okay.
So let's say one part of the fractal, whatever it might be, gets corrupted or damaged, whatever.
Right.
The system can still retrieve that data from the other 2 copies that are stored elsewhere on the fractal.
So if a cosmic ray hits our storage device, we're good.
I mean, in most cases, yes. I don't know what kind of cosmic rays you're dealing with, but in most cases, we're good.
That's amazing.
Because the code includes this really interesting averaging method during the decoding process. Yeah. So if one of those 3 copies deviates from the other two, the system is smart enough to say, hold on a second.
Something's up.
Yeah, and it can automatically correct it by using the other two. It's a very resilient system,
Wow.
especially when you consider how much data we were talking about storing. It really is a clever solution to this. One of the biggest challenges in data storage, right?
Totally. Yeah.
And I think what I keep coming back to is this really elegant idea of this fractal structure.
Yeah.
So we've talked about the resilience, we've talked about the efficiency, but how much can we actually hold on one of these things?
Yeah. What's the overall capacity?
That's what I want to know.
Right.
Like, are we talking kilobytes, megabytes, gigabytes, terabytes? What are we talking about here?
Yeah. Give me a sense of scale.
Right, exactly.
Right.
Well, the cool thing is the code actually calculates the theoretical storage capacity
Okay.
based on the complexity of the fractal, which is really neat.
Okay. So the more complex the fractal,
The more data you can store.
the more data you can store.
Remember how we were talking about how the canopy grows exponentially?
Yeah. Yeah. Like you're
Yeah.
adding those layers upon layers of branches on the tree, right?
Exactly. Like imagine that, but each one of those layers is holding a ton of data. With each layer, the number of those data points increases exponentially as well.
Okay.
And when you crunch the numbers, the code suggests that with just 1,000 iterations, we could potentially store over 374 billion bytes.
Whoa. Hold on. So you're telling me that with a structure, and correct me if I'm wrong here, built from just 1,000 points,
That's what we're saying.
we can store hundreds of gigabytes of data.
Potentially.
That's wild.
Yeah.
Okay. So that begs the question, how does this actually stack up against the way that we currently store data?
Yeah, that's the million-dollar question, isn't it?
Right.
I mean, it's theoretically possible that this could be a huge leap forward in storage density.
Okay.
But we have to remember, this is theoretical.
Right. Of course, it's all in the code.
It's a model.
Right.
Right.
Yeah.
So to really understand its true efficiency, we need to think about real-world constraints. And we need to compare it to what we already have, solid-state drives, or even some of this crazy stuff like DNA storage.
Yeah. Yeah, right. The more experimental stuff.
Right, exactly.
So the potential is there
The potential is massive.
for this vast storage capacity.
Yeah.
But it's still very early days, right?
Yeah, for sure.
I mean, we would need to compare, not just how much it can store, but how quickly we can access the data.
Right. Access speeds are huge.
Right. How much energy does it take to keep these things running?
Energy consumption, huge, yeah.
And of course, on the engineering side of things, can we actually build one of these things?
Right, like how do we even build these fractal storage devices?
Is it even possible?
Yeah, and that's where things get really, really interesting,
Yeah.
because you've got this really elegant concept, but actually making it work in the real world, that's the challenge.
Right.
That's the engineering hurdle that we've got to get over.
Is that where GPU acceleration comes in?
Yes.
Because I noticed that was mentioned in the code as well.
GPUs are going to be crucial for this, I think.
Okay.
Because remember what a GPU is. It's a graphics processing unit. It's literally designed to do these really complex calculations in parallel.
Right. It's what allows us to, render those beautiful graphics that we see in video games and stuff like that.
Exactly.
Okay.
And they're really good at it. They're designed specifically for this. And in this case, they'd be crucial for all of the heavy lifting of creating and managing and accessing all of this data on this fractal structure.
Okay, so it's not just about the storage itself then.
No.
It's about making it all work.
It's about the computation,
Right.
the computational power.
Having the computational power to make it all actually functional.
Exactly.
Yeah.
Because we're talking about potentially trillions of data points organized in this incredibly complex three-dimensional structure.
Right.
So GPUs would give you that raw power
Yeah.
to encode the data, to decode it, to do it quickly,
Make it all worthwhile.
to make it all actually work.
Otherwise, we're just, throwing data into a void.
Exactly.
And it just sits there.
Exactly.
Yeah.
You need to be able to use it and use it efficiently.
What I really love about this whole idea is that it really harkens back to this idea of biomimicry, right?
Totally. Yeah.
This idea that we're looking to nature
Taking inspiration from nature.
to solve our problems.
Yeah, because nature's already figured out.
Nature's got it figured out.
Millions of years of evolution.
Exactly. And so we're taking that playbook and we're applying it to, the digital realm.
And it works.
Well, we're hoping it's going to work.
Yeah, we're hoping it's going to work.
We're in the early stages here.
Exactly.
But it's an exciting prospect.
It's a really cool idea.
And what I think is so cool about it is that we're just scratching the surface of what we can learn from nature.
Oh, absolutely.
And this fractal approach to data storage, it's just one example.
It's just the tip of the iceberg.
Exactly. But let's kind of like shift gears just a little bit here and talk about beyond the technical details, what are the implications of this?
Yeah, the bigger picture.
The bigger picture, right? Like, where could this actually lead us?
Yeah.
It seems like one of those concepts that could have ripple effects across so many industries, you know?
Oh, yeah.
Like, I mean, we've talked about data centers, which is kind of the obvious one.
Right.
But what about, like, smaller devices? Like, could we use this to revolutionize how we store data in our phones or our laptops?
Potentially. Yeah. I mean, the potential is definitely there. Imagine having a smartphone that can hold like exponentially more data than
Mm.
anything that's out there right now.
Right?
Or, maybe it's not even based on the same kind of storage devices. Maybe it's a totally new thing.
Right, right. Like, it changes how we even think about storing data in those smaller devices.
Yeah, exactly. And because it's so fundamentally different, who knows where the research goes?
Right. It could go in a million different directions
It could go anywhere.
that we can't even anticipate.
Yeah, it's like a whole new branch of computer science just popped into existence.
Right, right. Exactly. And it makes me think about some of the other, emerging technologies that we've talked about on the show before. Like, what if you combined this with, say, DNA storage, which is another one of those things that seems like it's right out of science fiction?
Yeah.
Or even quantum computing. Like, what if you brought those ideas together?
Those are some really, really interesting possibilities.
Right.
Imagine, storing data within the very building blocks of life itself. Or, like you said, in that quantum world, that quantum realm, where things get really weird and wacky.
It's just strange to think about, I can wrap my head around it on one level, but on another level, it's like, what would that even look like?
I know, it boggles the mind, right?
It really does. It's like, storing whole libraries worth of information on something that's the size of, a grain of rice, or even performing the computations themselves within the fractal.
Right.
Like, it's not just about the storage.
It's wild.
It's kind of a natural progression of all of this, though, right? Like, we keep talking about storing vast amounts of information.
Yeah.
But it does beg the question, should we? Just because we can, does that mean that we should be storing this much information?
That's the question, Ron. I think that's one of those ethical questions that we really have to think about, because this technology, if it turns out that it works as well as we think it might, it comes with a huge amount of responsibility.
Right, because imagine, the implications for data security, data privacy.
Oh, massive.
If that kind of storage capacity fell into the wrong hands.
Yeah, you're talking about a gold mine of information.
Right.
So it's more important than ever to keep that stuff safe and secure.
And it's a good reminder that we have to, when we're exploring these really exciting frontiers of science and technology, you have to take the good with the bad.
Right.
You have to consider all of the implications, not just the, oh, wow, this would be really cool if. You have to think about the consequences as well.
Absolutely. And we've been talking about biomimicry, taking those cues from nature. And I think that's a really good principle to apply here, because nature is all about balance, right?
Right.
For all of its complexity and its efficiency, it understands limits.
Right. Nature understands that there are consequences to going too far.
Exactly. And we, as the architects of this new technology, we need to keep that in mind.
We need to bring that same mindfulness to the table.
Absolutely. We can't just get caught up in the excitement of it all.
Yeah, it's easy to get swept up in, this is so cool, and forget about the responsibility that comes with wielding this type of power. But that's, I think, a perfect note to end on today. We've gone from the intricate patterns of nature to the cutting edge of data storage.
It's been quite a journey.
It really has, yeah. We've gone everywhere today. And, as our society keeps generating more and more data, it's really critical that we explore these innovative, nature-inspired solutions, because they're more than just, intellectual exercises at this point. They're becoming a necessity.
I completely agree. We need to find new ways to address these challenges.
Exactly. So I would say to our listeners, as you go about your day today, take a moment to maybe look around and appreciate the elegant patterns that we see all around us in nature.
Yeah.
Because they're everywhere if you just take the time to look.
And a leaf, or
the leaves of a tree.
the spiral of a shell, a snowflake.
They're beautiful.
They're beautiful. And those simple designs often hold incredible complexity and efficiency.
And who knows, they might just hold the key to the future of how we store data.